Hello students, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 23 on the instruction sets of 8085 microprocessor part 2. In the previous session students, we have discussed some of the data transfer instructions extensively with the use of memory representation, as well as how we are going to understand how many machine cycles are required for a particular instruction. So with this knowledge, we would be able to understand the questions that would be available in the GATE exam very easily. Okay, so now in this lecture also we would be seeing more of the instruction sets of 8085 microprocessor. This session would include arithmetic operations, logical operations, there would be some branching operations and some special purpose operations. So let's start with this session. Now first of all we are going to see what are the arithmetic operations. Okay, so to understand arithmetic operations, there would be addition operation that can be performed. This would be the addition operation. Here you can see it is ADDR, that is it would be a register in register addressing mode. Okay, this would be in register addressing mode. It means that first of all, one thing that is to be understand that all the arithmetic operations are performed with accumulator, that is accumulator is used for arithmetic operations. That is, suppose this is the R instruction ADDR, it means we are adding the content of register R to the accumulator. Similarly, ADCR would means that we are adding the content of R to the content of accumulator, plus there would be an addition of carry, that is this addition is with carry. So similarly ADDM, it means that the data which is present in the HL register pair, the data the HL register pair is pointing would be added to accumulator. Similarly, this addition would be done with carry. Here ADI 8-bit data means this 8-bit data would be added to the accumulator. So you can see these all are register addressing modes. This would be indirect addressing mode because here we are not providing the address. Similarly, it would be in immediate addressing mode. Why these are immediate addressing modes? Because we are representing here the data. So these two instructions are for addition, these two rows are subtraction. Okay, so in subtraction there would be either subtraction without borrow or there can be a subtraction considering the borrow. So this would be with considering the borrow. This is the AND operation. This is for OR operation. This is for XOR operation. XOR operation. This is to compare the register with the content of the accumulator. So main thing is that we are doing all the operations, all the arithmetic as well as logic operations with the content of accumulator. So one thing that is very important is that here the bytes and the flags affect here the bytes and the machine cycles are not much important, but if we want to write, we can write it would be a 1 byte data and machine cycles involved would be only one, that is fetch, and there would be 4 T states. For this column the bytes would be 1 byte. Okay, but there would be 2 machine cycles, that is first it would fetch the opcode, second it would read the content that is pointed by the HL register pair. So there would be a need of memory read and there would be 7 T states. Similarly, for this there would be the 2 bytes of memory that is occupied by these instructions, these all instructions, and there would be fetch plus read because we have to read this data from the memory, and there would be 7 T states. So these are common for all the instructions that is present in this block. But the most important thing regarding the arithmetic and logic operations, that how the flags are affected. We have studied the flag register also, in which this is sign, this is 0, this is auxiliary carry, this is parity, and this is carry. Okay, so how these flags are affected is very important regarding the arithmetic operations. So you can draw this table, and with the help of this table we would be able to understand that which flags would be affected and what are the important flags that should be considered while doing this type of operations. So you can see that in addition all flags would be affected, and all the flags are important. That's why we have put the dash here. Similarly, for subtraction, all the flags would be affected, but the auxiliary flag should be taken into consideration very importantly, because there is a different way to check this auxiliary carry status. Okay, for and or operation, you can see all flags would be affected, and most important flags are AC, which would be at logic 1, and carry would be at logic 0. Similarly, for our operation, carry and auxiliary carry would always be 0. So these are constant flags for and or operation. Okay, this is for AND operation and this is for OR operation. For XOR operation, we can see that auxiliary carry flag would always be at logic 0. It means that they would remain constant for if we are operating these instructions, that is XRA R, or if we are comparing the data with the accumulator of this register, if we are comparing the data of accumulator with the data that is pointed by HL register pair, and if we are comparing the data with this 8-bit data, then flags would be affected, all flags would be affected, but auxiliary carry and carry flag would be always logic 0. Similarly, if we are comparing, previous instruction was the instruction to XOR these datas, but the next instruction is the compare. If we are comparing with R, the content of accumulator with register R, or if we are comparing the data of accumulator with the data that is pointed out by HL register pair, and if we are comparing the data with 8-bit data that is available in the instruction only, then all flags would be affected and auxiliary carry should be checked. Okay, so it is an important flag that should be checked after the instruction. Similarly, if there is an increment operation, you can see that only sign 0, auxiliary carry, parity would be affected and carry would not be affected. That is, it would store whatever it is storing previously. That is, in the previous operation, whatever data or whatever logic carry is having, that data would be retained. There would be no effect on the carry. Okay. So for increment, either it can be increment in the content of the register R, or it can be the increment in the content of M, which is pointed by the HL register pair, or it can be increment in the content of the register pair. So it is an indirect addressing mode. Similarly, for decrement, you can see that sign 0, auxiliary carry and parity would only be affected, and AC, that is auxiliary carry should be checked properly, and here also carry would not be affected. So carry flag would remain as it is. Okay, this is the meaning. And for rotate, we have only auxiliary carry would be affected, and we have for rotate only carry flag would be affected, and we have to check only carry flag properly. Okay, so for decrement, you can write DCR R if we are decrementing the content of register R. If we are decrementing the content of the M, which is the content pointed by memory, pointed by the HL register pair. So if we want to decrement that content, so it would be DCR M. And if we want to decrement the content present in this register pair, so we can use this instruction, that is DCX RP. One point that should be kept in mind for INX RP and DCX RP is that no flags are affected for this instructions. For these two instructions, there would be no flag that would be affected, that is, whatever the contents earlier present in the flag register, the same contents or the same logics or the same high level or low level logics would be present after this instruction also. That is, there would be no effect on the flags during these two instructions. So write quickly this table completely, because this is very important table. All the questions would be done with the help of this table only. Okay. And then we are going to study every logic, that is addition, subtraction, and how these important flags are taken into consideration would be checked. Okay. So the first instruction that we are taking is addition, then we go for subtraction. So there is no much importance or important point regarding the addition. We have to just do the addition and then we are going to check the flag registers. So to take an example, we are doing with ADI 6EH. What this instruction will do, it would add this content to the accumulator content. So suppose we are assuming that the content in the accumulator is 92. Okay, so you can add the content of these. So E plus 2 would be 14 plus 2 16, and in hexadecimal format there is no value as 16. So from 0 to 15, then again 0 with the carry. So answer would be 0 and there would be one carry present. So again 16, 0 would be the answer and carry would be generated. Okay, so this is our answer that is present inside the accumulator. And what would be the status of flag, students? The most important thing in the arithmetic operations is the status of flag. So sign flag, as this result is positive, so the sign flag would be 0. Zero flag, as the result is 0, the 0 flag would be set condition. Okay, and as this is don't care, so we can take 0 here. Then we have to check auxiliary carry. We can see that there is a carry generated after D3 bit to D4. Therefore we can say that auxiliary carry is also set. Then 0. Then we have to check the parity. You can see there are even number of ones present in this case, because the number of ones are 0, which is even, that is it is also in set condition, then 0 and then carry. No, so you can see there is a carry generated, therefore this flag would also be set in set condition. So you can see that what is the decimal equivalent for this hexadecimal equivalent, it would be 55H. So this is the status of the flag register, and this is the answer for accumulator. So this is the only way to do the addition and to check the status of the flags. Now for subtraction. Okay, so in the subtraction we see that auxiliary carry is given importance. So first you can write 2 points for unsigned operations. That is, we are doing an unsigned operations, that is there is no sign bit present, then carry flag would be 0 for positive result and carry flag would be 1 for negative result. Why we are saying carry flag would be 1 for negative result? Here you can consider carry as an borrow. So if the result is negative, it means we are doing the subtraction like this. Suppose we are doing the subtraction like this, then there is a need of borrow that should be taken from outside. That's why the carry flag is here set. And for sign flag we have to ignore it. Okay, now for signed operations, you can see sign, how we are going to solve the sign operations. So for sign operations, S, that is sign flag, would be 0 for positive result and 1 for negative result. Okay, and carry flag would be ignored. Okay, so this is the difference between this unsigned operation and signed operation. So we can take one example how we are going to do the subtraction process. Suppose there is an example which is given that the A is, suppose we have been given S we have been given an instruction SUBD. Okay, so what this instruction is doing, it is subtracting the content of D from accumulator, and we can see that accumulator, suppose we are taking the content as 85H and for T we are taking 32H. Okay, so what would be the subtraction here? 5 minus 2 would be 3 and 8 minus 3 would be 5. Okay, so from this we can comment on the all status of the flag registers, but because we can see that for this sign we have to ignore it. Okay, and for zero flag, as there is no so if we want to comment on the like this, so these are the flags, as the output is non-zero, so that Z flag would be reset. Here the sign flag would be 0, then again we would get 0. Now we have to check for auxiliary carry, then parity, then carry. Okay, so as there is no carry or borrow generated, so it would be 0, because for unsigned operation we know that for positive result carry would be 0. Okay, so this is 0. Now to check parity, we need to check what is the binary equivalent. It would be 0 1 0 1 0 0 1 1. So you can see that there are even number of ones, that therefore parity would be reset, parity would be set. So to check auxiliary carry, it is very important to understand the shortcut. Suppose the lower nibble of accumulator, check this, take this lower nibble of the accumulator and this lower nibble of the result. Okay, so you can write that if the lower nibble of the result, that is lower nibble, you can write here, I hope you have written this point. So if lower nibble of result is less than lower nibble of accumulator, then carry or auxiliary carry flag would be 1. Okay, so in this status or in this operation, we can see that the lower nibble of the accumulator is 5 and the lower nibble of the result is 3. As the lower nibble of the result is less than the lower nibble of the accumulator, then the auxiliary carry flag would be set. So this can be regarded as a shortcut. Okay, so it would be set else auxiliary carry would be 0. So here you can write 1. So this is the status of the flag register. Okay, So I hope you have understood the addition is subtraction process, how we are going to do the addition in the subtraction. You can write these points, then we are going to see and or operation. So the next operation before and or operation is increment and decrement operation. So you can understand increment operation first. If it is an increment operation, then we have studied that carry flag would not be affected, okay, and the result would be stored in the operand only. That is, suppose we are taking an example I and R, C with us, and what is the content of C? The content of the C is FF. So what would be the increment in C? There would be an increment of one bit in there would be an increment of 1 bit in the result. So FF plus 1 would give us result. So 1 plus F would be 0 and 1 would be the carry, and here would also be 0, 1 would be the carry. So you can see that carry is generated, but here this is the increment process. The instruction is increment. This is not an addition. If this was an addition, we would take the final result in of the carry that is generated in the flag register, but here we are representing it as a addition process, but internally there would be some other way to increment this the content of this register C. That's why the carry flag would not be affected, and therefore the most important point regarding increment is the carry flag would not be affected. Similarly, you can see for the, and we have also discussed that for INX RP, for INX RP, no flags would be affected. No flags would be affected. Okay. So if we are incrementing the content of the register where, then no contents would be, that is the status of the flag signals would not be affected. Similarly, for decrement process or decrement instruction, carry flag would not be again affected. That is, whatever carry is generated before this instruction would remain as it is after this instruction also. But if we want to understand if we want to understand this instruction analytically, we can write like DCR-C, where C, the content of the C is, suppose the content of the C is 90. So if we want to decrement it, we can subtract we can subtract 1 from it. So what would be the result? F, because we have to take a borrow, then as we have taken 1 borrow, it means 16 minus 1 would be F, and this would result in 8. So this is the answer that would be stored in this that would be stored in the content of this register as an answer. So what would be the status of the flag registers? So you can write, you can first draw sign flag 0, auxiliary carry, parity, and then carry bit. Okay, so what would be the bits? It would be 0. It would be 0 as the output is non-zero, so it would be reset. For parity, you can see that here would be 1 0 0 0 1 1 1 1. As there are odd number of ones, so it would be reset as carry is not generated or borrow is not taken, and but for we use say but you should understand here the point is that in decrement and increment, the carry is not affected. So whatever would be the previous carry would be shown here. So we are not here, we are showing here as not affected. And how we are going to calculate the auxiliary carry? In decrement, the rules of subtraction are followed. So if we can see, we can compare the content this of the operand and the result. So you can see that as the content of operand, as the content of result is greater than the content of operand, that's why this would be 0. Okay, and rest would again be 0, like this. So this would be the content of the flag register. Okay, so this is increment and decrement process. Now we are going to see logical instructions. So what are logical instructions? AND operation. So we have understood how we are going to do the AND operation, and what are the instructions for that. These are ANA-R, ANA-M and ANI 8-bit data. And you can also see that auxiliary, all the flags would be affected and auxiliary carry would be 1 and carry flag would be 0. So keep this in mind while doing an AND operation. So what is the purpose of AND operation? Used to mask the bits. AND operation is generally used to mask the bits. So the point to keep in mind, that is auxiliary carry would remain 1 and the carry flag would remain 0. So if you want to take an example, you can see that if we are using A and I, let us take A and I, and this would be FFH. Okay, suppose this is an instruction and the content of the accumulator is 0FH. Okay, so if you want to do the AND operation of these two bits, that is this content and this data of accumulator, you would be seeing that we know that how we are going to do the AND operation. This is our output. So 0 0 0 0 1 0 1 0 1, sorry, 1 0 0 and 1 1 1. Okay, so as all the bits, if you want to represent in binary equivalent, it would be like 1 1 1 1 1 1 1 1. Similarly 0 0 0 0 1 1 1 1. So it would be 1 1 1 1 0 0 0 0. So the final result would be 0 FH. Okay, so you can do from here only, as the contents would be same for this, it would be F, and as the contents are AND operated with 0, so it would be 0. So you can see that the answer is this, and this would be changed from 0F to again 0F. So you can see that here we have done the masking of the bits. So this is the AND operation. And what would be the OR operation? Suppose we want to do the OR operation, so the points that is should be kept in the mind that it is used to set the bits. That is, we know that for OR operation, if any one of the inputs is 1, the output would become 1. And here you should keep in mind that auxiliary carry and carry flag would be 0. Okay, so if we want to take an example, that is ORAB. Okay, and the content of A is 34 and the content of B would be CB. Okay, we are assuming an example, and this instruction would do the OR operation between accumulator and register B. So you can write this, and what would be its binary equivalent? It would be 0011 0100, and it would be C, that is 12, so 1100, and B would be 11, that would be this. So the OR operation would give us FF as a result. So while noting or while knowing the status of the flags, you just keep in mind that auxiliary carry and carry would be 0 and rest of the flags would be affected. Okay, so this is the AND and OR operation. Now you can see how we are going to perform the compare operation. Okay, so if we want to compare, there are some points regarding the compare operation. So here we are comparing the data which is present in the instruction, comparing the data with accumulator. Okay, so the points that should be kept in mind is that if the content of accumulator is less than the RM or the content of register or the data which is pointed by HL register pair or the 8-bit data, okay, then carry flag would be 1. Actually in compare instruction, the main thing is that we are subtracting the result from the accumulator, and you can see that if the content of accumulator is less than the data and we are doing this kind of operation, then there would be a borrow generated, or we can say a carry would be generated, or it would be necessary to do this operation. That's why here carry flag is set. Okay, and 0 flag would be 0 because there would be a non-zero result in it after the subtraction. Similarly, if the content of accumulator is equal to this data, it means that there would be no requirement of the carry, therefore carry flag would be 0, but 0 flag would be 1 because after subtraction of these two data, the content would in the accumulator would become 0. That's why behind the compare operation we are just doing the subtraction. Okay, but keep in mind that we are just doing the subtraction to understand it. There would be no change in the data of accumulator as well as there would be no change in this data. To understand what would be the status of flags, we are taking the help of the subtraction process to understand why the carry flag is 0 and 0 flag becomes 1. Similarly, if the content of accumulator is greater than the RM or 8-bit data, therefore carry flag would become 0 because if we are doing the subtraction like this and A is greater than R, it means that there is no need to avail a borrow or take a borrow from outside. That's why carry flag would be 0 and 0 flag would also be 0. That is, there would be a non-zero data available after this comparison. That's why these are the status of the flags that should be keep in mind while doing the comparison. Similarly, for complement, we use the instruction CMA and it performs the ones complement operation. Okay, here we are performing ones complement operation and flags are not affected. That is, to be kept in mind that no flags would be affected during this operation, that is complement, and the addressing mode is implicit as there would be no data or any address implicit. The addressing mode would be implicit because no data or address is present in the instruction, so that's why the addressing mode is implicit. If we want to understand with an example, so the content of accumulator is 1 1, and if we want to do its complement, that is its 1 complement, so what would be its 1 complement? How we are going to calculate its 1 complement? We know the shortcut. This is the binary equivalent, and if this instruction is present, that is CMA, we are going to take its 1 complement to take the ones complement of this binary result, what we are going to do, we just reverse the bits, that is 0 1 1 1 0 1 1 1. So the data that would be stored in the accumulator would be EEH, that is this data. Okay, so you are able to understand what is compare operation and what is complement. So you can write these points, then we are going to discuss the rotation operation. So let's see what is a rotation operation. So there are some points regarding it. The rotation operation is only possible with the contents of accumulator. So for content of accumulator only we can perform the rotation operation, and only carry flag would be affected. Okay, only carry flag would be affected, and sign 0, auxiliary carry and parity would be not affected. That is, whatever data it is storing, it would retain it. Okay, now we are going to see what are the rotation operations. First is RLC. It means rotate accumulator content 1 bit left without carry. Okay, this is the meaning of RLC. If the instruction is RAL, then rotate accumulator content 1 bit left with carry. So you can write these points, then we are going to see how the operation is done with carry and without carry. Similarly for RRC, rotate accumulator content 1 bit right without carry. Okay, that means in the rotation carry would not be included. And for RAR, rotate accumulator content 1 bit right with carry. Okay, this is the points regarding the rotation operation. Okay, so let's see one example, that is RLC. RLC is given, and content of A is given as 92H, and the carry flag initially is given as 0. So first of all we would put the contents of accumulator, that is 92H, that is 1001, and 2, that is 0010, and here we would represent our carry flag, that is 0. Now we know that with RLC what we are going to do, we are rotating the content 1 bit left without carry. That is, this content would come here, this content would come at this bit, this would become 1, this would become 0, this would become 0, this would become 1, and this would become 0. Okay, so what would be now the contents of carry as well as at this last bit? It is important to understand here. So this one would go in the carry flag also, and this one would also go to the LSB. That's why we are not here taking the carry flag. This is the meaning that we are performing the rotation without carry. The contents would be changed definitely. It would change from 0 to 1. At this bit would go into carry, but this bit also would go into the LSB, and the LSB would become 1. That is, rotation is done without the carry. Okay, and now let us take one example in which carry is involved. Okay, so if it is RAL and we are taking the content of accumulator as 87H and the carry flag initially is 0. So here we would take the carry in the rotation process like this. So initially you can mark the contents. It would be 8 and 7. Okay, these are the contents of the accumulator and this is the content of carry. So now we have to rotate the contents of accumulator to one bit left with the help of carry. So it would be 0 as it is shifted towards left one bit, 0 0 0 0. Here would be 1 1 1. Now this 1 would go to carry and this would be changed to 1, and this carry previous carry would come to this LSB. So the output would here be 0. Okay, that is this carry would come here as LSB and this MSB would come as would come to carry bit, and the carry now would become 1 and this 0 that is previous carry would come at LSB. So you can see here the rotation is done with the help of carry included in the rotation cycle, but in RLC we have changed the carry bit, but the carry bit is not included in the rotation cycle. The MSB itself come to the one bit left to LSB. So this is the way how we are going to do RLC, RAL, similarly RRC and RAR. So you can write these points. Then we are going to see some special purpose instructions. So I hope you have written this operation. Now we are going to first see some special purpose registers, some special purpose instructions. Then we are going to see the branching operations. So the halt operation is used to stop the execution of a program. Okay, and the number of bytes you required is 1 bit, and there would be two machine cycles with 5 T states. Okay, and here one more point is that buses are tri-stated or co-tri-stated after halt. Okay, these are the important points regarding the halt operation. Now the next operation is NOP, which is said as no operation. Okay, with the no operation we are just providing a delay. So if we want to provide a delay of some of around 4 T states, because it has 1 byte, 1 machine cycle and 4 T states involved. So if we want to give a delay of 4 T states in any program, then we can take the NOP, that is no operation instruction. Okay, so these were halt and no operation instruction. Now we are going to discuss HLLD. So LHLD 16-bit address. What is going to be done with this instruction? Okay, it will load the HL pair with the contents of 16-bit address, whatever content is present on 16-bit address, and the next address. Okay, with the help of this instruction we are loading the HL pair with the contents what are present in 16-bit address and the next address. So the bytes involved would be 3 bytes because there is a 16-bit address present. And what are the number of cycles? First cycle would be fetch cycle, that is taking the opcode from the memory. Then it would take 2 read cycles to read this data, that is this 16-bit address, and then again 1 read cycle to get the content from this memory location that is pointed by 16-bit address, and the next to transfer the contents of the next address to the HL pair, that is the lower address data would be transferred to L register by this memory read operation, and by the next data or the data present in the next address would be transferred to the H register by the help of this memory read operation. So there are 5 machine cycles involved, so there would be 16 T states. Okay, if you want to see an example, you can see one example, that is LHLD B600. So this is the example, and suppose in the memory representation at B600 data is 40 and at B601 data is 60. So what would be transferred in HL pair? So the lower bit address data would be transferred to lower bit, so it would come 40 here, and higher bit address data would come at the higher bit register, that is H. So this would be the content after LHLD process. Similarly, it would be SHLD. So it is just opposite of this previous instruction. Here we are loading the HL pair with the contents of 16-bit address in the next address, but here we are storing or transferring the contents of HL pair to the contents. We are storing the contents of HL pair. We can write the complete store the content of HL pair in the memory locations pointed by 16-bit address in the next address. Okay, so there would be a 3-byte instruction. First cycle would be fetch, then read, then write and write, because we are transferring the data from HL to these memory locations. So we need 2 write operations, 2 read operations, and 1 fetch. So the total T states would be 16 T states. Okay, so I hope you have understood these instructions. The next instruction is PCHL. So what this instruction is doing, it is transferring the content of HL register pair to the program counter. Okay, so you can see that from HL it is transferred to PC. So it would be a 1-byte instruction, 1 machine cycle would be involved, and there would be 6 T states that are required. Okay, so you can see that when we load the content of HL pair to this PC, that is program counter, the process or the execution that we are going within the processor would jump to this memory address. So you can say that it is a 1-byte unconditional jump instruction. So when we study what is a jump instruction, it would be more clear. So with the help of jump instruction, we can change the way of the process of execution. Okay, we can shift to another address. Similarly, you can see that whenever HL pair data is transferred to program counter, as program counter controls the flow of execution, so it would change the path, and now the execution would start from this memory address which is stored in HL pair. Okay, now we are going to see what is SPHL. So the contents of HL pair would be transferred to the stack pointer. Okay, so whatever data or whatever content is present in HL register pair, that content would be transferred to the stack pointer register. So it would be a 1 byte instruction, 1 machine cycle would be involved, and there would be 60 states. Okay, so this is SPHL. Now we are going to see what is XCHG. So in this we are going to exchange the contents of DE and HL pair. Okay, so the contents of, suppose the contents are represented with this like of DE, and these are the contents of H and L. So the contents of these would be exchanged, that is whatever is present in H would be transferred to D, and whatever is present in D would be transferred to H. Similarly here. Therefore, there would be the exchange of contents in a DE and HL register pair. So this is XCHG. So it would also a 1 byte instruction, 1 memories, 1 machine cycle, and 4 D states. Okay, now we are going to see XTHL. So what an XTHL is going to do, whatever data is present at the top of the stack, that is the data presented at the top of the stack would be transferred to the L register content. Okay, and the data which is present at the SP plus 1 memory address would be transferred to the H register H register. So with this we are able to copy it. Here we are doing the copy operation, that is the content present at stack pointer, that is the data at top of stack would be transferred to L register, and the data which is present in the next address of the stack pointer would be transferred to H content. Okay, but in this instruction there would be no change in the content of stack pointer, because stack pointer is a register in microprocessor and the stack is the content present in memory. This stack pointer points towards the top of the stack. Okay, so as there is a copy operation performed, therefore there would be no change in this data, that is the contents of stack pointer. Okay, but in the push and pop operation, when we were transferring the data, it is either pushed or popped. It means that the data is extracted completely and there would be a change in the content of stack pointer also. Okay, and what are the machine cycle involved in this instruction? First would be the fetch, second would be read, third would be read, fourth would be write, and fifth would also be write. Okay, so this is the machine cycles that are involved in this instruction. Now the ninth instruction is DAD-RP. So what is it going to do? It would add the content of register pair to HL pair. Okay, so there would be no change as there is a addition process is going on, but there is no change in the content of accumulator. It is just adding the content of register pair to an HL pair. Okay, so you can see we can perform with this instruction a 16-bit addition. Okay, because a register pair would be having a 16-bit of data, so with this instruction we can perform a 16-bit addition and only carry flag would be affected. In this operation only carry flag would be affected. Okay, and the result would be stored NHL pair only. Okay, and there it would be a 1 byte instruction with 3 machine cycles and 10 T states. Okay, so this is DAD RP. Now the last instruction is DAA, and with this help we can perform BCD addition. So we know what is a BCD addition. By this instruction we would able to perform BCD addition of the bits. Okay, so these were the special purpose instructions that we have studied: PCHL, SPHL, XCHG, XTHL, DADRP and DAA. So these types of instructions are sometimes used in the programming of microprocessor, and sometimes they are asked directly that this instruction is performing which type of operation. So I hope you have understood all the instructions, special purpose instructions you can write. Then we are going to see our jump instructions, that is the branching operations. Now we are going to discuss branching operations. So in branching operations, what we are going to do in this group, the control of the program is transferred from one location to another conditionally or unconditionally. What is meant by the control of the program? That is, suppose if any instruction comes like the branching operations, then the process of the execution would stop there. It would go to some another location, would complete all operations and then return to its main execution. So this can be done either conditionally or unconditionally. That is, when some condition would be satisfied, then only it would jump or it would transfer to any other location, or we can do unconditionally, that is for with no condition it should be transferred to that location. So the first branching operation that we are going to see is jump instruction. So jump instructions are used to transfer the program control from one location to another conditionally or unconditionally. Okay, so we are writing the conditions or the jump instructions for first conditional, that is if any condition would be followed then only it would jump, or second would be an unconditional instruction. So for conditional instructions would be J Z, that is jump on 0 flag, jump if result is non-zero, to 16-bit address, like this. This is the format, that jump if result is 0, then jump to 16-bit address. If jump if result is non-zero, to 16-bit address, like this. And jump if carry is generated to 16-bit address. So jump if no carry is generated to 16-bit address. Jump is if parity is set to 16-bit address. Jump if parity is reset to 16-bit address. Jump for negative number. Jump if result is positive. Okay, so this is for 0 flag. These instructions, the conditions that should be followed is for 0, this is for carry, this is for parity, and this is for sign flag. Okay, so with these conditions available in the instruction, then only a jump process to this 16-bit address would going to happen. So we can write 2 points regarding this instructions, that it would be a 3-byte operation because a 16-bit address would be present, and it would either take 2 machine cycles or 3 machine cycles. 2 machine cycles would be taken if the condition is false. If the condition would be false, it would take 2 machine cycles, that is 7 t states. But if the condition is true and it going to jump on the next address, then it would take 3 machine cycles, that is fetch plus read, because last read operation is to go to this 16-bit address. Okay, that's why there would be 3 machine cycles involved, and here it would be 2 machine cycles, and there would be 10 t states for the true operation. Okay, so these are the conditions that are available. For unconditional, it would directly jump to the 16-bit address which is present. So it would also be a 3-byte operation and would have 3 machine cycles, because this condition would be followed for every condition, because no condition is applied. So it would definitely jump to this address. Therefore, one read operation extra is required, and it would require 10 t states. Okay, so this is conditional branching operation and unconditional branching operation for jump instruction. So you can write these points. Then we are going to see very important example regarding the jump instruction that is frequently asked in the exams. Now let's see one example regarding the jump instruction. So we can see we are considering a jump instruction, jump if no 0 to 16-bit address. That is, if we are jumping, if the output or the result would be non-zero, and it would jump to 16-bit address. So this data would be acquiring 3 bytes of memory, 2 machine cycles if the statement or the condition is false, and 3 machine cycles if the condition is true. So let us take one example. Here it is a program written, a part of program in which it is memory address 6000H and MVI C,02H would be performed. That is, the 02 operation would be 02 data would be transferred to the C register. Now 6002H, because it is a 2-byte memory, so after 6001 at 6002H DCRC, that is, there would be a decrement in the content of the C. Okay, now 6003H is the jump condition, that is, if the result is non-zero, if the result is non-zero, then jump to L1. This L1 is referred as the label given to this address. We can write either 6002H also, but here we are using L1, and the last statement is halt. So how the process would commence, that first the data in C would be 02. Okay, now at DCRC the data would be decremented to 01. Now this condition would be checked, that if the data present is non-zero, yes, the data is non-zero. As the data is non-zero, it would transfer again back to this cycle. So there would be 3 machine cycles for this condition, because the statement is true, and the condition is true. So it would go back to this. Now again decrement would take place, 00. It would become 00. Now it come point at this point again. So at this address it would again check whether the content is 0 and non-zero. As the content is now become 0, it means this jump condition is now false. So it would come at this point, that is halt, and the final program would be completed. Okay, so there is a point we can see that the controlling register of a loop is register C. Here the controlling register is register C, that is, if C has n, that is, the data present is n. Here we are taking the journal view. The loop runs or executes or rotates for n times where the condition. Okay, so there are two data present. It means that it would run two times. The loop would run two times. So it would run for true condition for n minus 1 times. That is, if we taking 0, 2 as our data, so it would run one time as a true operation and one time as an false operation, because there would be a case that it would be false at any one time. So at one time it would work as an false condition, and rest of the cases and rest of the times it would work as an true condition. So here we can see that there are the data present is 0, 2, and we have also understood that the loop is run for true condition one time, and this loop or just this jump instruction is worked as an false for one time. So this is very important. Now regarding these jump instructions, the main point is asked is what would be the total execution time. So we can regard that total execution time is clock period, how much time is taken for one t state, into total number of t states into how many times that instruction is performed. So it would be regarded as count value. So now the total execution time is divided into two parts, that is TOL and TWL. So TOL stands for the time of instruction outside the loop. So there would be two parts of this TT. One is what are the instructions that are present inside the loop. So there are two instructions that are present inside the loop, and these two instructions, that is MVI and halt, are present outside the loop. They are not involved in the looping conditions. That why they would be performed only one time. These instructions, that is MVI and halt, would be executed only one time. That's why we have differentiated in two parts. Now what would be the total TOL, that is the time of instruction outside the loop. We know that f clock is 3 megahertz. Therefore the total time of one t state would be 1 by f, that is 0.33 microsecond. So 0.33, that is clock period, into total number of t states. For MVI there are 7 t states, and for halt there are 5 t states. Therefore 7 plus 5 would be 12, and when multiplication is done, the result would be 4 microseconds. The answer may be different, but you write the approximate and what is the correct answer. Okay, so we just require the approximate answer here. Now the second part is to calculate time of instruction within the loop. So how much time is required to complete this instruction which is within the loop. So it is again also divided into two parts, when the condition is satisfied and when the condition is not satisfied. So when for not satisfying a condition, it would be only one time. Therefore t into this condition would be satisfied, this not satisfied condition would be applied or would be executed one times. Therefore its count value is 1, and the t states for false application is, it would be executed. So 4 t states for this and 7 t states for jump instruction, because 7 t states are required for false condition. Therefore it would be t into 4 plus 7, that is 11, into 1, that is its count value. And this condition would be satisfied if we are taking the example of this operation only. If we are taking the example of this case, in this case the true condition is satisfied, that is the true condition is executed also for one time. Okay, so therefore t into 4 plus 10, that is 4 for DCRC and 10 for this condition, for jump condition. So these are the t states for the satisfying conditions, and this would give result are TWL. So the total time executed is 12.33 microseconds. Here the count value for satisfying can be changed. It can be n minus 1 times depending on the value that is present in the controlling register. So what point we have concluded is that in the total execution time, TOL would remain same because it is outside the loop. TNS, that is the case for unsatisfying condition, would also remain same because it would be executed only one time. The change that is having in total execution time would be only TCS, that is how many times the condition is true, that only would be changed, and it depends on the data, okay, which is present in the controlling register, which is controlling the loop equations. Okay, so this is the complete example regarding the jump instruction. So quickly write these points. Next we are going to see our next branching operations. So the next branching operation is call. So with the help of call instruction, it is used to call the subroutine within the main program. Suppose there is a separate program which is known as subroutine, which is written in some other place. So if we want the use of that program in our main execution, in our main program, we can use the call condition. So it can be used conditionally or unconditionally. So thus these conditions are same as the jump instructions. The point to be noted is that it would be a 3-byte instruction. If the condition is false, it would be 2 machine cycles, and there would be 9 T states. Okay, and for 5 machine it would be for false condition, and it would be for true condition. Okay, and for true condition, if the condition of the call is true, then it would run for 5 machine cycles and 18 T states. So this is for conditional. And for unconditional case, call 16-bit address, that is whenever there would be the statement, it would go to this memory location, and at this memory location whatever separate program is written, it would be executed first, then it would return to the main program. Okay, so it is also a 3-byte instruction. It would have 5 machine cycles because first would be required for fetch, second 2 would be required to read this address, and then write, and write operation is required because we are transferring the content of program counter which is next to the stack. So these points are important, that's why we are using 2 write operations. So the total time or total T states would be 6 plus 3 plus 3 plus 3 plus 3, that is 18 T states, and this is the highest for any instruction. Okay, these are the highest T states possible in 8085. So when the point important regarding the call instruction is, when a call is executed in the program, the content of the program counter or the address of the instruction next to call, that is if the instruction for call is 6000H, the memory address is 6000H, and after 3 bytes, that is 1, 2 and 6003, this data would be transferred to the stack, so that whenever the call operation or the separate program is executed completely, it would return to the main execution of the program. So the program, as a program counter controls the flow, that's why we are transferring the data, that is this, to the stack pointer so that it can be revived again. Now the control of the program would be transferred to the subroutine address. When this data, that is the next address after the call in the main program, is transferred to the stack, whatever address which is present here in this call statement would be loaded to the program counter, and the execution of that separate program would start. Okay, so this is the call instruction. You can write these points. Next we are going to see how we will able to return from the separate program to the main program with the help of the return instruction. So students, you will be finding these instructions quite complex, but don't worry, these are very simple instructions. When you will see the programs, it would be you would be able to do that questions easily. Okay, so this is the call instruction. These 2 points are important. When call is executed, the content of program counter or the address of the instruction next to the call, that is the instruction next to the call is this, its address would be transferred to stack, and the control of the program is transferred to the subroutine address, that is this 8000. Now how to return from the call program to the main execution with the help of return statement. Okay. So the definition is when return instructions are used as the last instruction of the subroutine, which is a separate program which is executed with the help of the call instruction or interrupt service routine to return to the main program. So there is a possibilities of conditional return and unconditional return. For unconditional return, it would be 1 byte, and this is for false and this is for true. So for false, it would be 1 machine cycle and 6 T states, and for true it would be 3 machine cycles and 12 T states. Why 3 machine cycles? Because the data or the program in the previous instruction, that is call, what we have done, that we have transferred the instruction next to the call to the stack. Okay, we have transferred that address to the stack. So to revive that address from the stack and to again load to the program counter, there is a requirement of 2 read operations. That's why for the true condition, or we can say for the unconditional operation, there is a requirement for 3 machine cycles, or we can say 10 T states. So the points regarding the return is, for the step 1 would be the data present at the top of the stack. What data is present at the top of the stack? The instruction next to the call. The memory address next to the call which is present in the stack, which is loaded to program counter. So that would be loaded to the program counter, and the control of the program is now transferred to the 16-bit address that is loaded to the program counter, so that the main program can be executed. So this is the use of the return statement. Okay. So you can write these points. Next and the last instruction we are going to see is the software interrupt instruction. We have already studied what is software interrupts, that is RSTN, and how we are going to use it we will see. Okay. So I hope you have written this statement. The last statement is RSTN, and RSTN operation is similar to the unconditional call. So we have understood whenever a input output device requires the surface of the processor, it requests with the software interrupt, or we can say that in other words, whenever there would be a program and an input output devices requires the service, it would jump to that service or that separate program or the ISR that is stored for in this RST to avail the services of the processor to the input output devices. Okay, so this can be regarded as an unconditional call, because in the unconditional call statement or the instruction, we have also transferring the program counter, or we are transferring the execution from main program to another separate program. Okay, so it can be regarded as a 1 byte unconditional call. Okay, so it is 1 byte or 3 machine cycles are involved and 12 T states are involved. So when RSTN is executed, step 1 is that program counter value is pushed into the stack. Okay, it is just similar to clock just similar to the call statement, and in the call statement also we are transferring the program counter value to the stack, so that whenever we revive from the separate program and return to the main program, we can execute our main program from the next step, that is after call statement, or here after the RST end statement. And the program step 2 would be program control is transferred to the vector address. Here the vector address, the program counter would be loaded then to the vector address, and then separate program is executed. So these two steps are involved in RST, and we have studied what are the steps involved in return as well as the call statement. So I hope students you have understood all the instructions that are required in microprocessor. In the next session, which is the last session of this digital electronics subject, we would be studying some interfacing which is done in the microprocessor, and how the memory addresses and how we are able to find the memory addresses, our initial and the final addresses in the memory. Okay, so thank you.